carbonyl bonds are happy and stable. What that means is anytime you unform a carbonyl, nature wants to reform the carbonyl. That's kind of been implicit in our whole discussion here, because all the reactions we've been seeing, again, on carboxylic acids and acid derivatives have been attacking the carbonyl, but then nature doesn't just sit around and accept that you've destroyed the carbonyl, it tries to reform the carbonyl. That was the key pattern in all these addition eliminations. We've been attacking and then reforming the carbonyl. Nature likes carbonyls. If you unform a carbonyl, nature will try to reform it. So the driving force for this step is nature doesn't mind putting the negative charge on this oxygen too badly because it allows it to reform this carbonyl. That's why all these carboxylic acids and acid derivatives go through addition elimination. The only reason that aldehydes and ketones don't do this is because they don't have any acceptable L group. So they can't reform the carbonyl. But with an electronegative element here, it's good enough that we can reform the carbonyl. Okay, so this is actually a pretty poor leaving group, but it's acceptable to kick it off to reform the carbonyl. Now, we're not done. This is not the final product. This is a little tricky. Does anyone have any idea what would happen next? It's pretty hard.
We attack another molecule that would act as a base, making it enolate.
Okay, excellent. Oh, maybe it wasn't that hard.
All
right.
It ends as an enolate, right?
That's right. That's right. So what you did there was very good. Is you focused on the reactive atom. This has the charge, so this is the reactive atom. If anything else is going to happen, this is the guy that's going to make it happen. Now, this is confusing because theoretically this could be either a nucleophile or a base, but you correctly saw in this situation it will act like a base.
Because we already have, because attacking it wouldn't do much difference.
Yeah, if it attacked, it would just replace one ester with the same ester. That wouldn't be a trans-esterification, it would be an identical esterification. So actually what we should say is probably to some extent this will attack nucleophilically, but we don't care about that because it doesn't change the outcome. It just gives us the same ester that we started with. So we're not interested in the nucleophilic attack by this. You guys correctly saw this could act like a base, and who's it going to deprotonate?
Alpha H in between both.
This one. Why will it deprotonate this alpha carbon and not this alpha carbon?
Because that H is really acidic due to resonance structures in between.
Yeah, I think we talked about that in our last session. An alpha carbon that's between two carbonyls is even more acidic because there's even more resonance structures. Okay, so let's show that last step. Okay, so now we have a special type of enolate. What is it that's stabilizing this negative charge? Well, not only is there a resonance structure where you can put the negative charge on this oxygen, there's another resonance structure where you can put the negative charge on the right-hand oxygen. In fact, it looks like you guys might have actually drawn one of those resonance structures. Again, I prefer to put the negative charge on the alpha carbon, but you could also draw the resonance structure where the negative charge is on one of these oxygens. So that would be fine too. People tend to forget this, but this is an important step. This is not a minor detail. And by the way, this is the other driving force that allowed us to kick off this poor leaving group. The other driving force is that it's very favorable to deprotonate this particular alpha carbon here. So that was the other driving force for this reaction. This reaction wouldn't happen if we couldn't do this last step where we deprotonate this alpha carbon. Another way of putting it is, where would the negative charge rather be? On this oxygen or on this alpha carbon? Well, it would much rather be on this alpha carbon because of the double stabilization by resonance. That's another strong driving force for this reaction. What that means is, and this is likely to be tested, the only reason this reaction can work is because this alpha carbon has enough hydrogens to deprotonate twice. It needed to deprotonate once to become a nucleophile, and then it needed to deprotonate again in this last step here. So the Claisen condensation can only happen if there's an alpha carbon with at least 2 hydrogens. Claisen condensation can only happen if there's an alpha carbon with at least 2 hydrogens. At first it seems like it only needs 1 hydrogen to become the enolate, but it needs a second hydrogen so it can deprotonate in the last step, because that's a major driving force for this reaction.
And if it doesn't?
Then you just don't do the Claisen condensation. All of these steps are equilibrium steps, like I've drawn them. And the thing that can tend to favor the forward reaction here is, again, this last step, where we deprotonate this alpha carbon. All right, here we had plenty of hydrogens because we had 3 of them. Okay, so as I said, Claisen condensation is when we have a deprotonated alpha carbon attacking the ester. So we have an addition-elimination reaction. We just follow the same patterns like we did before. Now, what type of compound do we have here? Well, one good way to name this is a 1,3-dicarbonyl. That's the name of the whole chapter, right? This is a 1,3-dicarbonyl. That doesn't point out that it's actually a 1,3-dicarbonyl where one of the carbonyls is an ester, but the general name here is 1,3-dicarbonyl. The whole chapter here is about 1,3-dicarbonyls. Well, they start by telling you how to make 1,3-dicarbonyls. The Claisen condensation is how to make 1,3-dicarbonyls. Soon we'll have to talk about what you can do with 1,3-dicarbonyls, but the first thing we have to learn is how to make them. So the Claisen condensation is a good way to make a 1,3-dicarbonyl. Okay? Okay, if you want, you can go through the whole mechanism here, but if you want, you can just try to draw the product without the mechanism, whichever you like.